doubts and all is there. Okay. And once we are done with that, I have a little bit of theory items that I have to discuss. Basically, we will proceed ahead with prime numbers and some properties. So in the last class, we had covered Euler's phi function, right?
Yeah.
Phi function we had seen, and before that, we had also seen Euler's theorem. A power phi m is equal to 1 mod m, right?
Yeah.
Is congruent to 1 mod m. And we had also seen Fermat's little theorem. So Fermat's little theorem, phi function, and Euler's theorem. These are the things that we have covered so far. We want to go ahead to properties of prime numbers. And properties of prime numbers will basically mean that we'll be discussing things like Goldbach conjecture and twin prime conjecture and stuff like that. So that is probably the topic of next class maybe. And I have a missed class, so I'll cover that up in the next coming week. Okay. So probably I will do another class on Friday or Saturday, which will be a theory class. Today we can discuss just the problems from problem set 3 and 4. Okay. So let me know on the group if you're free on Friday, Saturday evening.
Yeah.
Okay. And right now, let's just discuss problem set 3 first, because we have not yet covered that. So problem set 3, have you attempted?
Yeah, some of the questions I attempted.
Okay, so for example, the first question, first two parts should be fairly easy, right?
Yeah.
So did you get any answers for question number 1, part 1? This is 105x plus 121y is equal to 1.
Yeah, I got 46 and minus 53 as x and y respectively.
That's correct. X is minus 53 and
yeah, 105 coefficient is minus 53 and 121 coefficient is 46.
Correct. So this is the straightforward, the method that we had learned, reverse of Euclid's division algorithm, right?
Yeah.
Reverse of Euclid's division algorithm gives you this one solution at least. So similarly, the second one is also a big one, but it can also be done. So if you have the answer, tell me. 1, 2, 3, 4, 5 x plus 6, 7, 8, 9, 0 y
11 comma minus 2
is equal to 15, right?
Yeah, 15.
So 11 comma minus 2 comes by the same method. The interesting question in this one is the third one, which is 6x plus 15y plus 20z is 1. So how do you solve an equation with 3 variables? 6x
by
plus 15.
Grouping together, like grouping of 2, then forming like that, I guess.
So what is the first step? What will you solve first here?
6x plus 15y
is equal to what, you will say?
GCD, equal to their GCD
so
of 6 and 15.
So you can say 6x plus 15y is GCD of 6 and 15, so 3, right?
Yeah.
And this will have some solutions, right? So one of the solutions for this is 3 comma minus 1, right?
Yeah.
It is obvious from looking at it also that 3 comma minus 1 is satisfying, right? Correct.
Yeah.
Now, since 6x plus 15y is equal to 3, right? That has some solutions, right? So you can say that some multiple of this, right? So 3w plus 20z is equal to 1, right?
Yeah.
That is the next equation that you can solve, because this will either be 3 or it will be some multiple of 3 here, right?
Yeah.
Correct. So now my next equation can be 3w plus 20z, right, is equal to 1, right? And basically you will get that w should be 7 and z should be minus 1 from here.
Yeah.
Right? Correct. So 6x plus 50. Okay. So now what you can say is you can rewrite this now. This equation itself can be rewritten as this is 3 is 6x plus 5y, right? 15y, 6x plus 15y, right? So you have basically 3w plus 20z is equal to 1, right? So now what you can say is 6x plus 15y into w plus 20z is equal to 1, right? Correct.
Yeah.
This equation has the solutions x is equal to 3, y is equal to -1, w is equal to 7, and z is equal to -1, right?
Yeah.
Because we have already found the equations that solve this, and we have already found solutions which solve w and z, right? Correct.
Yeah.
So the equation can be rewritten basically as 6x times w plus 15y times w plus 20z is equal to 1, right?
Yeah.
So the equation, the original equation was notice 6x plus 15y plus 20z is equal to 1. So now you can say that small x must be the xw and small y must be the yw and small z is equal to z only, right? So this becomes
Yeah.
xw becomes 21, this becomes -7, and this becomes -1. Correct.
Yeah.
So basically, what was the idea here? You solved the first two coefficients and said what is it equal to, right? And whatever it is equal to, this will be 6x plus 15y is GCD of that, so it will be 3 or multiples of 3, right? So we
Yeah.
called that 3 multiples of 3 and solved this one, right? And then rewrote this equation like this, right?
Yeah.
Correct. Instead of 3, I wrote 6x plus 15, right?
Yeah.
Makes sense. So the second question I think is just generalizing this, right? No, the fourth question.
Yeah.
So basically, like we can analyze what happens in the fourth question. So it is saying under what conditions on A, B, and C is it true that the equation AX plus BY plus CZ is equal to 1 has a unique solution?
Yeah.
As a solution. Describe a general method if you want to find the solution, right? So, so the condition when they will have a common solution will be when, remember the previous example where we had 6x plus 15y plus 20z
Yeah.
is equal to 1. Now,
GCD of 6 and 15
we took GCD of 6 and 15 and that was 3, and then 3 and 20 was 1, right?
Yeah. So
So
GCD of
basically,
A, comma B.
Basically you are saying that
Yeah, and then GCD of GCD of A, comma B and C, like that, I guess.
GCD of A comma B comma C, but what will be the GCD of A comma B comma C here? 6, 15, 20 should be 1 only.
Yeah.
Yeah, because nothing it is divided, right? GCD of 6, 15 and 20 is 1, right?
Yeah.
Correct. So it looks like there is a condition that ABC GCD should be 1, right?
Yeah.
That makes sense because if ABC GCD is equal to D, right? Then D divides LHS, right?
Yeah.
But D cannot divide 1, right?
Yeah.
Obviously, there cannot be anything which is a common factor, no? Otherwise, you will be able to say that D will divide 1, right?
Yeah.
Correct. So how do you find the solution if you have the condition that A, B, C have no common factors? Basically, this ensures that there is a solution. This ensures there is a solution. But how to find that solution? Do the same thing we did earlier. let's say AX plus BY is equal to G, right? And G is equal to GCD of A and B, right?
Yeah.
Then because A, B, C have no common factors, right? Therefore, that means G and C cannot have common factors, right?
Yeah.
That is correct, no? Because G has common factors with A and B, but then it cannot have anything with C, then, right?
Yeah.
So now what you have to solve is solve for this. G times W plus C times Z is equal to 1, right?
Yeah.
And then put back AX plus BY times W plus CZ is equal to 1, right? So find the
Yeah.
solutions for X here, Y here, W here, Z here, right? And then put it
Yeah.
back like this, and then say that A times XW, right? Plus B times YW plus C times Z is equal to 1, where XW will take the X answer, YW will be the Y answer, and Z will be the Z answer, right?
Yeah.
So that is the general way of solving a linear equation in three unknowns, right? Where you have no common factors between the coefficients. Correct?
Yeah. So if there are more unknowns, so we can follow the same
Same method, you
strategy.
have to extend the same
Okay.
process. But hopefully they will never get a situation where more than three there are there. But that's the same method. Like you have to just do it, right?
Yeah.
Now, question number 2. Suppose that GCD is 1. Prove that for every integer C, the equation AX plus BY plus C, BX plus BY is equal to C has a solution. We already know how to do this, right?
Yeah.
37x plus 43y is equal to 100. We know how to do it, so we'll not discuss this one.
Yeah.
This is again by the Euclid's method, right? You know how to do, right?
Yeah. Yeah.
Find one solution, then try to extend it, right?
Yeah.
Then try to extend it by taking many cases, like, right?
Yeah.
So question number 4, find all incongruent solutions, right? Find all incongruent solutions. Basically, all solutions to that congruence you have to find. Were you
Yeah.
able to get that?
Yeah, I guess I was able to get it. 14k plus 6. I
So
got
let's do
right.
some of the answers we can check once.
Yeah.
Question number 4 is 1 second. It is 8x is congruent to 6 mod 14. Part 2 is 66x is congruent to 100 mod 121. Mod 121. Part 3 is 21x is equal to 14 mod 91. Okay. And what we want to find out here is all possible incongruent solutions. Basically, solutions that don't give the same remainder when you do modulo whatever is being mentioned in that problem.
Yeah.
So, okay. So first job is to find out okay. So tell me what answers you got for first one.
First one I got 14k plus 6.
6 mod 14 you're saying.
Yeah.
There is one more solution. The first one
Mm,
is 6 mod 14 is correct. There is one more type of solution, which is 13 mod 14.
14.
Just check once, 14k plus 13, right? Let's say 8 times 14k plus 13, right? This becomes what? This becomes 8 into 14k plus 8 into 13 is 104, no?
Yeah.
And that is 8 into 13 is 104, correct? And 14 sevens are 98, no? See?
Yeah.
8 into 14k plus 1, right? Plus 14 plus 6, right?
Yeah.
So this is also working out, right?
Yeah, but how to find it? Actually, I use this one. 8x minus 6 is equal to 14y, and then this one.
8x minus, that is correct only. 8x
Yeah,
minus 14y is equal to 6, right?
yeah,
So, okay. So you are solving the equation 8u minus 14v is
yeah,
equal to 6.
yeah,
So 8u minus 14v, first you should solve GCD of 8 and
yeah,
14 is
2.
2, right?
Yeah,
This solution, if you find, then what will come here solution? You will come 2 comma 1, right?
yeah, 2 comma.
2 comma 1 is the solution of this. Okay. But you have to multiply by 3 times, right?
Yeah, 6 comma 3.
So 6 comma 3. So you are getting 8x. X should be 6 and y should be 3, right?
Yeah,
Okay. Then okay, 8. So clearly 6 mod 14 is coming, right? 8
yeah,
into 3, 8 into 6 minus 14 into 3 is equal to 6, right?
yeah,
We're getting 8 into 6 is equal to 14 into 3 plus 6, right?
yeah,
So x should be basically 6 mod 14,
yeah,
right? That is coming.
yeah,
We can also 6 mod 14 has come. This is also 6 plus 7 is 6 plus 7 is 13 mod 14. How can we get the other root? If it was 13, 6 plus 7. What is a nice way to get the other root? 14. Eight into 6 is equal to 6. Okay. 2 comma 1 comma 3 is the solution. Okay, so 14k plus 6 fits this. We know 14k plus 13 is also fitting this. But why is it fitting? Because
because of polynomial roots p modular theorem, we know that more than one is coming. Would come in.
polynomial roots theorem, right now this is a linear only, no? But because it is not a prime, right?
Yeah,
More than one is possible.
yeah,
More than one is possible if it is not a prime. But we are not able to immediately, I mean, it's just said that the answer is this. Like he has not shown any method and all. The
yeah.
answer is this and it works out correctly. But right now I'm unable to find a way to get it properly. Why? Why is 13 mod 14 coming? Wait. Solutions are 6. Oh, correct. See, remember, how do you generalize the solutions? You do 6 plus m by g, no?
Yeah,
Once you find one solution to this, how do you generalize the solutions? You remember? If you can find x1, y1 that satisfies the first equation, You can
Yeah.
generalize by doing x1 plus k times m by g, no? And y1
Oh,
minus k times m by g, something like this.
yeah.
You remember?
Yeah.
So,
Yeah.
so k is basically 1, let's say, and m is 14 and g is 2, no?
Yeah.
So you get 6 plus 7, 14, 13 is also working. That is also a
Okay.
possible solution. So you should revisit the video. I think we discussed this generalizing in a previous video, right? When we
Yeah.
were solving that congruence in second class or third class, right?
Yeah.
Go back to that video. I had also forgotten, but you can generalize from x1, y1 to get a finite number of roots, right?
Yeah.
So that is what he's doing. That is why he's doing 13 mod 14. You understand?
Okay. Yeah.
This m by g factor you can add, and k can be 1, 2, 3, so on, so on, right?
Yeah. Yeah.
Okay.
Yeah. Got it.
Just go back to the one class ahead again and look at through that section again, okay? After the class.
Yeah.
So,
Because this type of question, I got only one answer because of it.
so you could get possibly more answers if you remembered this part,
Yeah.
right? So in the second part, let's look at the second part. What are the answers that you got?
Yeah. I got only one answer. No, it was no solution. Yeah.
Okay, wait 1 second. Second part was 66x is equal to 100 mod 121. Okay. So GCD of 66 and 121 is 11,
11.
but it
Yeah.
does not divide 100,
Yeah. So no
right?
solution.
So there is no
Yeah.
solution. So the condition on this was this congruence AX is equal to C mod M. What was the condition? GCD of A and M should divide C.
Yeah.
Then only you will get solution. But in
Yeah.
this case, it doesn't happen, so no solution. Third part is 21x is equal to 14 mod 91.
Yeah. Again, I got one solution. 91k plus 84.
Okay. So you got
X is minus 8.
minus 8. So your question was what? Question was 21x is equal to 14 mod 91, right?
Yeah.
21x is equal to 14 mod 91. So your equation should have been 21x minus 91y is equal to 14,
Yeah.
right? Okay. Now, look, you can divide, first you can solve 21u minus 91v is equal to 7, right?
Yeah. 7.
91v is equal to 7. So this will clearly have a solution, and you can basically actually divide by 7 again, or you can find the solution 9 and 2, right? Positive solutions I would look for.
9 and 2. Okay.
Like first divided by 7 once, right? So
Yeah.
you can just get 3u minus 13v, right? Is equal to
Yeah.
1, right? Now clearly you can see that 9 and 2 will fit, no?
Yeah.
Right?
Like for 7, I got this thing. For like 7, when it was equal to 7, I got.
That is the same equation, so same roots will work, no?
Yeah.
I mean, this is the same equation as this, right?
Yeah.
So 9 and 2 is the root of this, right?
Yeah. But I got some other roots.
You got negative, right? Something.
Yeah. I got negative roots.
So that's also fine, I'm sure, but ideally I would not like negative, right? I mean,
Okay.
you don't want to write minus 8 mod n, right? Because it can be expressed in a positive way also, right? The same thing.
Yeah.
If you write minus 2 mod 5, right? You can just say plus 3 mod 5.
Yeah.
You understand?
Yeah.
So ideally, I would not like to write negative. So I want to find a positive answer. That's why I'm going for a large value. 9 and 2 is the correct solution, right?
Yeah.
Once you get 9 and 2, the equation's solution here will be just 18 and 4, right?
Yeah.
Something like that, no? 18 and 4 it should become, right?
Yeah.
So 21 into 18 minus 91 into 4 21 into 18 minus 91 into 4 is equal to 14, right? So
Yeah.
x is equal to 18 mod 91 is coming, right?
Yeah,
Because it is 91 into 4 plus 14, right? And 21 into x is 18, no?
Yeah.
You are understanding? No?
Yeah.
So x is equal to 18 mod 91 has come. Now, that is not the only solution. Okay, this is one
Yeah.
solution. So other solutions will be obtained by adding other solutions. Just note down this point. Other solutions can be obtained by adding multiples of 91 by GCD of 21 and 91, right?
Yeah.
Adding addition of multiples of m by g basically. M is 91 by g, right?
7. Yeah.
And g is 7, right? Correct.
Yeah.
So basically GCD of 21 and 14, A and C, right?
Yeah.
So that is GCD of 21 and 14, which is 7. So 13, right?
Yeah.
So you
30.
can say 18 plus k times 13, right? So what I'm saying is 31 will also be a root.
Yeah.
Okay. 44 will also be a root when you add 26, right?
Yeah.
Then what else will be a root? 3 times 30.
57.
57 should also be a root.
Yeah.
39
70.
plus 18. And then 4 times 52. 70 should also be a root. And what else? 5 times
83.
60. 83 should also be a root.
Yeah,
After that,
83.
you don't want to write.
Yeah, I got 83 only actually, minus 8.
Actually, and 96 is also a root. Actually, 96
Yeah, 5.
actually 5, right?
Yeah.
96 will come if you do
Minus
6
30.
times. 6 times, right?
Yeah.
6 times 13 plus 18, right?
Yeah.
Correct. So 96 mod 91 is basically 5 mod 91.
5 only. Yeah.
Right? So you are getting 5, 18, 31, 44, 57, 70, 83. Right?
Yeah.
These are the numbers that are positive and less than 91. Those are the solutions. You can check, it will come. Okay, check for 31 or something. It will be true. Okay.
Yeah.
So the idea is one solution once you get, if you had gotten the 96 one or whichever one you got, right? 83 one, right?
Yeah.
After that also you can add multiples of m by g, right? And then you will
Yeah.
get all the others.
Yeah. 30.
Okay.
Yeah.
Okay then. So this is how you do this one. Hopefully question 6, 5 and all will also be similar, right?
Yeah.
You can do that. Question 6, 5 and all will be similar. So now let's go to question number 8. Okay.
Yeah. So in the x square ones question, we have two
X square one.
values, right?
Let's do question number 7 then. Okay.
Yeah.
Question number 7 is x square 1.
No, I mean the question number 5C part onwards.
Question number 5C part. Wait. X square is equal to 1 mod 8 and all, right?
Yeah. So maybe we can add 7, like add multiples of 7 to form a square number and then take it there to the other side.
See, x square is equal to 1 mod 8 and 2 mod 7 and all, no? He
Yeah.
had told that there is a method where you can just check values till 1, 2, 3, 4, 5, 6, 7. No?
Yeah.
So this is just verification, trial and error, okay?
Yeah, but
Because
we can
then,
also do like this also, right? X square, like since there is 2 written and on the right side, we can do 7 plus 2 is equal to 9, then x square minus 9.
1 second, what are you doing? X square is equal, which one are you solving?
The D part.
X square is equal to 2 mod 7.
Yeah.
So right now what has to happen is x square should be 7k plus 2, right?
Yeah.
So what are you saying now? Tell me.
Yeah, we can do like 7k plus 2, then
We can do plus 7.
Yeah,
And
plus 7 and then 9. Then it will be a square number. So
no,
we
but
can
no,
show x plus
no,
3
it will
in
not work because how will it work? X square is equal to 2 mod 7 you have. So basically you have x square should be equal to 7k plus 2. Now tell me what?
x square is equal to 9 mod 7. Like that. And we
You
can
will,
find solutions to x plus 3 into x minus 3. It's congruent to
no,
0.
how are you converting it to 9 mod?
Yeah, we can add 1, right? Like assume like 9.
You are adding what here? Both sides, what are you adding?
No, I'm not adding both sides actually. Like 9 is congruent to 2 mod 7. That's why I'm just replacing 2 with 9.
9 is congruent to 2 mod 7. Okay. So you're just replacing this with 9
Yeah, to get the
mod
square
7.
number.
Okay. You are saying x square is equal to 7k plus 9, right?
Yeah,
Mod 7.
yeah,
So basically 9 mod 7, you say.
yeah,
X
9
square,
mod 7.
x square is 9 mod 7 unit.
Yeah,
Okay.
then x
Okay,
plus
that
3 and
is,
x minus 3.
then what are you doing?
Then x plus 3, x minus 3. Like we can take 9 to the left side. X square minus 9 is congruent to 0 mod 7.
X square minus 9 is divisible by 7.
Yeah,
So x plus 3, x minus 3 is divisible by 7. No,
yeah, one of them must be 7.
that's 7. One of them must be 7. So 4 it can be,
Or yeah,
it can be 10, right?
yeah, 10 as in 3. Yeah,
Okay, okay, this is possible. However, what he meant, I think, is just check the values. Okay, just check the
okay,
values till 1, 2, 3, 4, 5, 6 and see whether x square is becoming 2 mod 7. Okay.
okay,
So for small numbers, you can do that. Later, we'll discover other ways to solve these types of questions. Don't stress about it right now. It's fine.
okay.
Let's go down to the more interesting ones, which are, I think, question number 7, I think, right?
Yeah, 7.
Okay. Okay. Question number 7. How many solutions are there to this congruence? So obviously, you'll have to think of something here because the polynomial looks a little complicated, right?
Yeah, actually, I factorized it first
Hmm.
and then simplified it and then found something.
So what did you factorize it? How?
Yeah, actually, I forgot the way I
Okay, one
done
second.
2 weeks
Let's
back.
try it once now. So the polynomial is written as x power 4 plus 5x cube plus 4x square minus 6x minus 4 congruent to 0 mod 11, right?
Yeah, I actually guessed 1 as a solution, I guess.
1 is fitting, yeah? 1
Yeah,
plus
1 is
5
fitting.
plus 4, 10 minus 10. Correct.
Yeah, using that we can factorize it.
It is fitting. So you can factorize it how? X cube, x minus 1, right?
Yeah,
Minus x cube plus 6x square, x minus 1, minus 6x square plus 10x, x minus 1, minus 10x plus 4, x minus 1.
yeah,
So x minus 1, and it becomes x cube plus 6x square plus 10x plus 4 congruent to 0 mod 11, right? This part,
yeah.
let's see if we can factorize. Minus 2, is it working? Minus 8,
Yeah, actually,
minus 20.
that's
It is
what I
working.
put the value.
It is working. Okay. So
Yeah,
let's see this plus 2x squared, so plus 4x, x plus 2 plus 8x, so plus 2 x plus 2, right?
yeah,
So it becomes x plus 2 common, x minus 1 and this is x squared plus 4x plus 2. Now it is not factorizable.
Yeah, now it is not factorable.
So you are getting this 0 mod 11. So clearly x will be 1 should satisfy, right? 1 mod
Yeah.
11. That should satisfy, and minus 2 should also satisfy. So
9,
that means 9 should satisfy.
Yeah.
9 mod 11, right? And since 11 is a prime, you cannot have more roots than 4, right?
Yeah.
And right now this seems like not factorizable, right?
Yeah.
So let me just check once what is happening in the book. 1 and 9, he's saying it has 2 solutions. Okay.
Yeah.
So what happened is basically there are fewer than 4 solutions. This happened because first of all 11 is a prime. So this is fitting the polynomial roots mod p theorem, right?
Yeah.
Now part B is saying the congruence x square minus 1 is equal to 0 mod 8. How many solutions does it have? Now this one, because it's a small mod, no, mod 8, you can just check 1 to 7. Okay.
Yeah, 4, I guess.
There are coming 4 solutions for this.
Yeah.
So the solutions are 1, 3, 5, 7.
Odd numbers, yeah.
Right. And it does not contradict the polynomial roots modulo theorem because
8
P
is
is not a prime. Right.
Yeah.
Correct. So this is fine. So I think more or less this exercise is done. Question 9 is formats theorem only, I think. Formats
Yeah,
little
third
theorem.
part I couldn't do actually.
Which
Of
one?
seventh question. Third part of seventh.
Seventh question, third part. Let P and Q be distinct primes. What is the maximum number of possible solutions to x square minus a is equal to 0 mod PQ? Okay. Okay.
Yeah.
Okay. Let's take some examples, right? We can take some distinct primes and see what happens. Let's take the smallest situation, 3 and 5, right?
Yeah.
3 and 5 are 2 distinct primes. You have to get x square is equal to 1 mod 15, right?
Yeah.
X square is congruent to 1 mod 15, right?
Yeah.
Now, if you check, 1 is a root,
Yeah.
right? 2 is not a root. 3 is not a root. 4
11 would be, I guess.
4 is a root, right?
Yeah. I guess
4
11
square is 16, right?
Yeah.
11 is also a root, right? Let's see anything before that. 5, 20, no, 6, 6, no, 7, 7, no, 8, no, 9, no, 10, no, 11, okay. And let's see, 12, 144 is not working out.
135 is no, I don't know.
144 is not working out. Then 13,
No,
169 is also not working out. 14, 196 might work out. Yeah. See, 196,
Yeah,
right?
14.
180 and 195, right? So there are 4 roots coming, right? Correct. So in this problem, you can get the answer by just checking this once, right? The answer is 4. The proof that more than 4 is not possible is slightly complicated. More than 4 is not possible. So I would recommend that do one more case, okay? 3 and 7 you can do, right?
Okay.
3 and 7 you can do and convince yourself that 4 is the answer, right?
Okay.
You could have found the answer. The proof is a little hard that there cannot be 5. Okay. So we'll probably discuss it later. It uses pigeonhole principle. So right now, I don't know if I can discuss this right now. Okay. So we will do the proof of this later, but getting the answer is possible, right? You got 4. You will get, if you check x square is equal to 1 mod 21, you will get 4 again. You just have to find those 4. Okay.
Okay.
So, okay. Then in problem set 3, what else is there? 9 and all would have been fine. No? 9.
9 actually, 9 I couldn't do. Wilson's theorem, it's it.
It is Wilson's theorem.
Yeah, but the proof I cannot do. Couldn't do.
Okay, one second. 9 point question 9. So calculate the value of p minus 1. Isn't the proof the same as Fermat's little theorem stuff? Exactly, take a, 2a, 3a, and so on. One second, let me just check. Okay. No way, maybe it is not the same. So it's called Wilson's theorem. The answer that you should be getting is what? P minus 1
Yeah.
factorial is equal to congruent to minus 1 mod p, right?
Yeah.
This is the answer, and this is called Wilson's theorem.
Yeah.
Now, let's try to prove it. Okay. We have to prove that p minus 1 factorial is leaving a remainder of minus 1 when you divide by p, right? So, okay. We know for every value of a from 1 to p minus 1, we know that we can solve this equation ax, this congruence ax is congruent to 1 mod p. As long as a is less than p, you will always have GCD of a and p is 1, right?
Yeah.
I mean, not necessarily, but it will not divide this. Like there is possible one solution here.
Yeah.
Correct. So we can find a solution to that congruence. Now, what we have to find out is can we if x was a mod p, right? Here, if x was a mod p, then you would have gotten a square is equal to 1 mod p, and then p will divide. So if you had here x was a mod p, right?
Yeah.
In if x was a solution and x was happening to be a mod p, then that would mean that it will become a square is congruent to 1 mod p, right?
Yeah.
Right? And then you can say that a square minus 1 is congruent to 0 mod p.
Yeah.
So basically a minus 1, a plus 1. P must have divided a square minus 1, right? P
Yeah.
divides a square minus 1. So P divides either a minus 1 or a plus 1, right? Correct.
Yeah.
So, okay. So P will divide a minus 1 or a plus 1. So, if you have numbers, let's take some actual prime number and think about it, because right now it is very hard to think. So let's take P is 7, right? For now.
Yeah.
Okay. So I am looking for values between 1 is less than equal to a is less than equal to 6. 1 to 6 such that this happens, right?
Yeah.
And I am searching for x is equal to a mod 7, right? And I have gotten 7 divides a minus 1 or a plus 1, right?
Yeah.
So if you look at all the numbers from 2 to 6,
Yeah.
right? All the numbers from 2 to 7 minus 2 to 5 actually. 1, 2, 3, 4, 5, 6. So look at the number 2 and 5, right? Uh, can you pair up numbers so that the product is 1 mod p somehow? Can you pair up two numbers here whose product is 1 mod p? Oh, wait, 2 and 4, right? 2 and 4
Yeah.
is 8, which is 1 mod p. 3 and 5 is 15, which is 1
15.
mod p.
Yeah.
Right? Correct, correct. So you are getting two pairs at least, right?
Yeah.
Between 2 to 5, right? So between 2 is less than equal to a is less than equal to p minus 2, right?
Yeah.
Correct. This is p minus 2, this is 2, right? So you're not touching the numbers 1 and p minus 1, right? Correct.
Yeah.
So between 2 to p minus 2, all the numbers are, you can pair them up and both of them product is becoming 1 mod p, right? Right.
Yeah.
So now multiply all of the numbers once. 1, 2, 3, 4, 5, 6, basically till 7, right? Before 7,
Yeah.
right? And you can
Yeah.
say that 1 into p minus 1 into this part is 1 mod p, this part is 1 mod p, right?
Yeah.
So it is 1 only, no?
Yeah.
So this whole number is 1 p minus 1 mod p, right?
Yeah.
Correct. This whole
Yeah.
number is p minus 1 mod p, and actually it should have been p minus 1 factorial, no? Basically p
Yeah.
minus 1
Factorial.
factorial is the number that you got, right?
Yeah.
And that is having the same modulo p as p minus 1 only, right?
Yeah.
Right. I think we are close right now. And let me just think. Oh, wait. Oh, so we are getting that p minus 1 factorial is same as p minus 1, no?
Yeah. Then minus 1 mod.
Same as p minus 1. So p minus 1 is just minus 1 mod p, no? Then,
Yeah.
right?
Yeah.
Okay. So the idea here is basically that we know that there is a solution like this. Ax is equal to 1 mod p, right? So if there is a solution like this, we are looking for solutions of x which are a mod p. For every value of a such that a lies between 1 to 6, you can basically find pairs which become 2 into 4 is becoming 1 mod p, like this. 1 mod p here.
Yeah.
Let me think. I'm a little unconvinced still. For every value of 1 to p minus 1. Hmm. Hmm. So in the question, what was he saying? Exercise 9.2 asked you to determine the value of p minus 1 factorial mod p, where when p is a prime number. Now he's saying compute the value of m minus 1 factorial mod n for small values of m that are not prime. Okay. Do you find the same pattern as you found, right? Okay, this is 9. This is the next question. The previous question is compute p minus 1 mod p for some small values of p, find a pattern and make a conjecture. So right now, by checking some values, you will find that it is always minus 1 mod p.
Yeah.
And proving, he's saying try to discover why p minus 1 factorial mod p has the value it does for small values of p, and then generalize your observation to prove the formula for all values of p. So basically, p minus 1 factorial, when it is a prime number, 1, 2, 3, 4, 5, 6, right? If p was 7, right? This is the thing. This is the product that we are looking at, right? And
Yeah.
mod P, we are looking at it, mod 7. So what we have just discovered is that there are groups of terms here, which are mod 1 with respect to this, right? There
Yeah.
are 2 into 4 is 8, which is 8 is same as 1 mod 7. And 3 into 5 is 15, which is equal to 1 mod 7, right? And those terms, basically all of those terms cancel out, and what is left is just first term and last term, right? So it is just P minus 1, which is equal to minus 1 mod P, right? Now let's look at some other prime numbers also. If you look at 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right?
Yeah.
So let's look for those pairs which give 1 mod 11, right? Correct?
Yeah.
So you will see that
2 and 6.
1 into, no, 1 you will not be touching,
Yeah, 1 won't be.
and 10 also you won't be touching. You will be looking for pairs between 2 and 9, okay?
Yeah.
So 2 and 8, 2 and 7, 2 and 6, see?
Yeah.
2 and 6 is giving 1 mod 11, right? 3 and 4
Yeah.
is giving 1 mod 11, right? 5 and 7 is 35, right? 5 and 8 is 5 and 7
5
is
and
30.
9.
5 and 9 is 45. 5 and 9 is a good pair, 1 mod 11, right? And 6 and 8 is 48, right? 6 and 7, oh, wait, 1 second. 6 is already taken, so we cannot use that, right? 7 and 8 is
7 and 8.
56, right?
Yeah, 56.
So this is the pattern that he wants you to discover, that why it is becoming this, right? Because you are noticing that every time you are getting pairs like this, right? All the internal terms, all the terms from 2 to P minus 2, you will always be able to find pairs which are such that the product of them is 1 mod P, right? Are you getting it?
Yeah, but why do we find such pairs? Like,
Why you are finding such pairs is because you are getting a solution to this congruence. What is this congruence meaning? Ax minus py is equal to 1, right?
yeah.
This congruence has a solution for sure, and some of the solutions are of the form of x is equal to a mod p. Because some of the solutions of this are of the form of x is equal to a mod p, when you put it here, it becomes a square mod p, right, is equal to 1 mod p, right?
Yeah.
So you're getting a square minus 1 is equal to 0 mod p, which is what we said. Product of two of those numbers are becoming 1 mod p. So
Yeah.
you will always find a solution to this for a is less than p, and some of the solutions, which are basically the pairs that you're finding, are looking like this. That's why products are becoming, a square is becoming 1 mod. You understand? The reason for the
Yeah.
pattern is that you are being able to find solutions to this congruence. And once this congruence, the solutions you write down, some of the solutions are turning out to be a mod b.
Yeah.
Okay, so it is better to understand it by examples. Okay, take some examples and see if you are convinced. Take some other prime number, right, 5, and see if you are seeing that some of the solutions of this congruence are becoming like this. Okay.
Yeah, 2 into 3.
So just try it once and see, you will get convinced. Okay. 1 second. What else is there? Question 10 and all is fine. No? 10. We had already
10
discussed, I think, this one, 10th one.
Yeah, 10 we have discussed.
Yeah. So problem set 4 is left. We will do problem set 4 in the next class. I have to actually stop right now. So we will do problem set 4 and we'll go ahead in the theory of prime numbers. Okay. in the next class.
Yeah.
And next class will be on Friday, Saturday. I will let you know once, like Saturday most probably. Okay, Saturday
Okay.
if you are free.
Yeah, I'm free on Saturday.
So Saturday evening we'll do a next class. We'll do problem set 4 and we'll go ahead in the theory. I want to cover the theory a little faster because we missed 1 or 2 weeks. Okay.
Yeah.
Okay. That's all for today. I'll see you then on Saturday. Just
Thank you,
try
sir.
out problem set 4 also once, and
Yeah.
I will try and update the assignment also by then. The next assignment I will send, assignment number 5, which will be the concepts that we'll discuss on Saturday. Okay.
Yeah.
Okay. That's all for now then.
Yeah.